We are continuing on here in section 8.7, factoring a difference of two squares. Here we have a perfect square, 16x squared, and a perfect square, 81. And we're finding the difference between them. We're subtracting. So we're still going to set this up. Difference of two squares means our signs are going to be different. And we're going to find the numbers that can multiply to these pieces. So to multiply to 16x squared as a perfect square means it has to be 4 times 4 for the 16 and x times x for the x squared. 81 is 9 times 9. And because we don't have any middle term there, we don't have any linear term in our polynomial, our outsides and insides have to be opposites, so we can't have different values. They have to be the same, the square values here. So 9 and 9 and 4 and 4 with my x's there. Again, we can FOIL this back to double check if you'd like. Firsts, outsides, insides, lasts. 36 minus 36 is 0, and I get 16x squared minus 81. Again, if you weren't sure, we could have factored this the same way that we had before, plus 0x minus 81. But when we try to swing our 16 here, we get numbers that are big and hard to work with. It's hard to find our factors there. So if we can recognize that this is a perfect, the difference of two squares right away, it makes it a lot easier in the long run. Now, feel free to pause here and give this a try if you'd like. Right now we have a perfect square, 25d squared, minus a perfect square, 64. So we can set this up as the difference of two squares. Since we're finding the difference, our signs are going to be different. 25 is 5 times 5. And d squared is d times d. So 5d times 5d is how we get to 25d squared. 64 is 8 times 8. And again, those have to be the same factors in order for our outsides and insides to be opposite and add up to 0, which is what we have here. We don't have any linear terms there. So 5d minus 8 times 5d plus 8 is the factored form. Remember, factors are things we multiply together. So here we just have two things multiplied to get to our 25d squared minus 64 in standard form. If we look at B, though, this one's a little bit different. We have a perfect square and a perfect square, but we have to find the difference of two squares, not the sum. Here, this cannot be factored. Because if we wrote this out, 25d squared plus 0d plus 64, there's nothing that multiplies to 64 and adds to 0. We can subtract to 0 like we just did here, but we can't add to 0. So this one cannot be factored. So make sure that it's the difference of two squares, meaning a subtraction sign instead of addition. That's very, very important. In example 5 here, we are going to completely factor this out. Anytime we factor, we want to check for a greatest common factor first. Okay, we always have to take out what's common if anything is common. So here between 24 and 6, 24 is 6 times 4, which is 2 times 3, and 2 times 2. And we have g squared. 6 is 2 times 3. And it's negative, so negative 1. So I have a common 2 and a common 3. I multiply those together, and 6 is my greatest common factor. We take that 6 out, just like I just did here. And what we have left is 4g squared in my first row minus 1. Factored out what's common there. Now, inside my parentheses, 4g squared is a perfect square and 1 is a perfect square. So I have the difference of squares, and I can factor this down further. 4 is 2 times 2. G squared is G times G. And 1 is 1 times 1. And since I multiplied to a negative number, my signs have to be different. Since I found the difference of two squares, my signs are going to be different. And this is our final answer in factored form. Again, if we want, we can multiply this back to double check. 4g squared, outsides positive 2g, insides negative 2g, lasts negative 1. 2 minus 2 is 0. Remember, that's still being multiplied by the 6. Now we distribute that 6 in. 24g squared minus 6, which is what we started with. So our answer is correct. Again, every factor still needs to be accounted for. Okay, we still have to be able to multiply all the way back to our original, so we need that 6 in front. Just for it to be completely factored, that's not in our factors in parentheses. Our differences of squares there are product and sum, or product and difference. It's outside, in front, being multiplied by the whole thing. Now, feel free to pause here and give this a try if you'd like. What is the factored form of each expression? Again, our first step when we factor is to factor out what's common. So, 12 is 4 times 3 and 2 times 2. So here I have 2 times 2 times 3 times t times t. 48 is 6 times 8, 2 times 3, 2 times 4, and 2 times 2. So I have a 3 in my 3 column, a 2 in my 2 column, another 2 in my 2 column, 2 more 2's, so I make 2 more 2 columns, and a negative, so a negative 1 column. What's common is a 2 times a 2 times a 3, which is my greatest common factor, which here is 12. So I take that 12 out, it still needs to be accounted for, and I multiply by what's left. In my first polynomial, I just have a t squared left. In my second, I have a negative 4. Here, again, anytime we have a binomial with a squared term and a constant term, we're going to try and factor it as a difference of squares. And here I can do that because t squared is a perfect square, t times t, and negative 4, okay, since we're subtracting, that means my signs are going to be different. Finding the difference, different signs, and now I just worry about my 4. 4 is a perfect square, 2 times 2. So 12 times t minus 2 times t plus 2 is 12 t squared minus 48. We can FOIL this back to double check. T times t, t squared. Outsides plus 2t. Insides minus 2t's. Lasts minus 4. 2 minus 2 is 0, so I have t squared minus 4. And again, these are still being multiplied by 12. So when I distribute that in, I get 12t squared minus 48, which checks with where we started, so our answer is correct. In B here, again, first step, factor out what's common. So 12, we have a 3 here, which is prime, so as long as we check, can we take a 3 out of everything? Yep, we can go ahead and do that right away as well. If you want to list it out like we did here, you certainly can. But if you recognize, like here, my smallest number is a 3. Can I take a 3 out of everything evenly? Yep. So I'm going to go ahead and do it that way here. For those of you that have been trying to do it there. If you're not sure though, go ahead and write out your steps using your trees here. When I take that out though, remember, even though we divided it out, it still has to be accounted for, and it goes in front. I have 4x squared left plus 4x plus 1. Here, we're going to try and factor inside our parentheses. I have a perfect square for my first term and a perfect square for my last term. So there's a potential that this is a perfect square trinomial. I'm going to check. 4x squared is 2x times 2x. 1 is 1 times 1. Now, I have to double check the middle term. So I multiply my two factors together, and then we double it, and I get 4x, which checks out in the middle. So I drop down the sign from my middle term and square it. we can check this. Take 2x plus 1 times 2x plus 1, or we can use our shortcut, square it, multiply them together, and double it. Okay, but if you want to FOIL them out just to double check to make sure you had the right pattern, go for it. (4x squared) plus 4x plus 1. Now keep in mind we still have this 3 here that we need to distribute in, and these are the same, so I'm only going to do it once. 12x squared plus 12x plus 3. Again, once you got to this point here, if you wanted to do it, we want a swing method. Multiply to 4 it would be, and then add to 4. You sure can. Just keep in mind we always have to factor out our greatest common factor, because otherwise when we divide with our swing method, that factor will cancel out and it'll be like it wasn't there, and we won't be able to multiply back to our original here. So our final answer here for factored form is right here. Real quick recap here. Some trinomials, such as squares of binomials or differences of two squares, can be factored by reversing the rules for multiplying special case binomials. And that's all I have for section 8.7.